Still using the equation of the previous discussion, 4x plus 6y minus 5z plus 12 equals 0. Recall that we determined that the point 0, negative 2, 0 does lie on this plane, and here's that point along the negative y-axis. If x equals y equals 0, what do we get? Well, not going through the details of the equation, it should be clear that both x and y are 0, so we get negative 5z equals 12, so that z equals 12 fifths, and that gives us the point 0, 0, 12 fifths. Now 12 fifths is about 2 1/5. That will lie along the z-axis. And let's represent that point as being about here. If y and z are both 0, then the y and z terms go away, and we end up with 4x equals negative 12, so that x would be negative 3. So x equals negative 3 might be about here. The point negative 3, 0, 0 would also lie on the plane. So we could draw this triangle with this side going behind the z-axis and sort of represent at least part of the plane. Now we want to ask a question about another point. Let's take a point, about here. Now where is that point? Well, let's say that point lies a little bit above the xy plane, so that its y coordinate would be here. Its x coordinate would be back here, and I didn't draw this projection line correctly. I'm going to just kind of X that out. So the y coordinate will be about here, the x coordinate here, and the z coordinate will be this far below the xy plane, which will put it an equal distance below the origin about here. So we could estimate the coordinates of this point. Okay, the coordinates of this point, let's see, if this distance is 2, this might be about, that's probably not 4, but let's call this 0, 4, 0 here. This point may be 1, 0, 0. This point on the z-axis may be negative 0, 0, negative 1. So that this point here would have coordinates 1, 4, negative 1. Now I want to ask the question is, how far is this point from this plane? So what's the distance of the point 1, 4, negative 1 from the plane 4x plus 6y minus 5z plus 12 equals 0? To determine that distance, we can draw a vector from any point of this plane to any point of this plane. And let's just choose as a convenient point the point on the z-axis, 0, 0, 12 fifths. Now this vector will be what? It'll be 0 minus 1, which is negative 1, 0 minus 4, which is negative 4, and 12 fifths minus negative 1, well, that's going to be 12 fifths plus 1, and that's going to give us 17 fifths, about negative 1, negative 4, 3 1/5. Let's make those braces pointy to indicate that this is a vector, and for good measure, let's put an arrow over the top of it. And in I and j terms, that would be negative I minus 4j plus 17 fifths k. Now, this vector is not perpendicular to this plane. At least I seriously doubt that it's perpendicular. But let's remember that we can read off a vector that is perpendicular to the plane, namely 4x plus 6y minus 5z, and we can see how much of this vector is in fact perpendicular to the plane simply by projecting this vector onto the normal vector. It might help to see a picture of that. And this is just a picture that depicts the situation. We have the vector here, that's our vector, negative I minus 4j plus 17/5 k. And then we have our normal vector, which is 4I plus 6j minus 5k. Now, I'm not even going to attempt to put that in a correct direction, but maybe the vector would look something like this. So here's our normal vector, equal to 4I plus 6j minus 5k. Now we want to know what the distance is from this point to this plane. That distance is going to have to be measured at a perpendicular to the plane, meaning that it's going to have to be measured along the line of this normal vector. And to figure out the distance, all we have to do is project this vector at a right angle onto this vector, and this vector will have a magnitude that's equal to the distance from the point to the plane. So the length of this vector is the distance from the point to the plane, and we're going to determine that by simply doing a scalar projection of this vector onto this one.